Okay, class. Okay, so can you hear me? Guys?
Yeah.
Okay. Okay, class. Okay, so we call back. So what we learned about op-amp the last class, just a recap. We go very fast to the earlier one. Okay. So what we learned about the last class is we talk about the electronic. This is electronic. Electronic is a very important part of our life. I think your computer, your phones, everything is electronic. Electronic is good because the size is small. All the chips are getting smaller, so the size of the device getting smaller. So and it's very efficient. It's very efficient. So the system of electronic works from these three departments we discussed that day: sensing device, processing unit, and output device. That day we done with sensing device, and we halfway of doing processing unit now. Later, maybe the next 2 hours later, we're going to be like output device, maybe on Tuesday, if I'm not mistaken. Okay, sensing device, we learn about what? Got 4. What are they? LDR. So first we learn about LDR, thermistor, piezoelectric transistor, strain gauge. LDR, recap very fast. LDR is what? Light intensity rises. Light intensity rises. What? Resistance decreases. Therefore, voltage across LDR will decrease in potential divider circuit. For thermistor, temperature rises. Resistance decreases, so voltage decreases. Okay, these two something new. As I told you, piezoelectric transistors testing what? Pressure. When pressure rises, then the voltage will rise across the piezoelectric transistor. You know, the potential divider, one will be the fixed resistor, another one will be the sensor, will be the LDR. One of them, one of these 4 will be fixed here. So for piezoelectric transistor, if pressure here rises, the voltage across the voltage across the piezoelectric transistor will rise. Pressure. We're going to talk in depth in ultrasound later for piezoelectric transistor. Strain gauge, as I said, strain. Strain rises, and of course the resistance rises because the wire get more thinner. Therefore, resistance rises. Therefore, voltage across the strain gauge will rises. So all sensors will be placed in a potential divider technique, and the input will send to where? The op-amp. So this is what we learned that day. So we skip this, strain gauge and everything. Then, as I said, it's going to be used as a potential divider to send the signal to the op-amp. Okay, what is op-amp? Op-amp is act as the brain of the electronic circuit, and it amplifies the signal and decide whether to on or off the output. It gives the output whether to on alarm or to off alarm, or maybe a street light, all decided by this chip. Okay, then we talk about 5 property, which is very important. It has infinite input impedance. It has infinite zero output impedance, no resistance at all. It means what I'm trying to say is, for operational amplifier, the input impedance is very high. That means the current technically is 0, go to the into the op-amp, and when it come out, the output impedance is 0. Therefore, output current is technically like is infinite. Okay, so infinite impedance, 0 output impedance, infinite gain. So infinite gain, what is gain actually? As I told you, output over input is gain. Normally, according to ideal, this op-amp is infinite, but in reality, how much? It's going to be 10 to the power of 5, the gain normally. And bandwidth. Okay, what is bandwidth? A range of frequency. Ideal operation amplifier has an infinite frequency response and can amplify and frequency so that it has to be an infinite bandwidth. So any frequency you input into the operation amplifier, it can amplify it without any disruption. But in reality, the op-amp really have a bandwidth. If the signal exceeds the bandwidth, what happens? The amplification won't go to the desired level. Okay, let's say the amplification say 50, have to increase by 50 times. But if we out of the bandwidth, then it won't amplify it for 50 times. It might amplify it to maybe 25 times. So it's a big problem. Okay, if you exceed bandwidth. So infinite bandwidth for ideal op-amp, and finally the infinite slew rail. This all we learn. Then we talk about the formula followed by the what you call ideal operational amplifier is this formula. If positive greater than negative, output will be positive. If negative greater than positive, negative output will be negative. So inverting input is the negative input. Non-inverting input say to be positive input. Okay, so this is a power supply. Okay, then we talk about saturation. Saturation. When the output operational amplifier decided a big voltage, but the output will be supplied by the power supply. Power supply can't afford to give that voltage asked by the operational amplifier. The supply will give whatever it has. If it's 10,000, but the supply only 10 positive 10 volt, the output will be positive 10 volt. Okay, this is called saturation. Okay, so this is a small recap. Okay, now today's lesson is this circuit. Okay, this is very important part, turning point under this topic. Okay, look at this circuit. Let's try to understand this circuit. Okay, this circuit power supply is connected side. So please see here, this is R and this is R. This is another resistance F, and here they place the LDR sensor. Okay, LDR sensor. Okay, let's say I give a number here. Let's say the voltage Vs, let's say I give you 10 volt. It's 10 volt. Here also, let's say it's 10 volt. 10 volt. This is positive 10 volt. So if I give here 10 volt, what is the potential here? Positive 10 volt. So potential here will be positive 10 volt. So potential here and here will be, as usual, same, positive 10 volt. Both are positive 10 volt. But when crosses the resistance, when come to this point, what is the voltage here will be? Because this is earthed. This is called sign of earthed. So the potential here will be 0 volt. These two will be 0 volt. So positive 10 become 0 volt after crosses the two resistance. Okay, now question is, can anyone tell me, this is a potential divider, the potential divider, this is up R, down R. Okay, so what is the voltage at this point will be? Anyone? So positive 10 becomes 0 here after crosses R and R. So after crosses 1 R, the potential here will be how much? Positive 5 volt. Correct? Everyone agree? Positive 5 volt. Because R going to divide the voltage equally. So this first R take 5 volt, the second R takes 5 volt. So it's going to drop by 5. So the balance is 5 volt here. So the input for negative will be how much? 5 volt. The input at what you call inverting input will be 5 volt. Okay. Okay, now anyone? I just want to put some question here. Okay, I go to the whiteboard. I go to the whiteboard. Sorry, temporarily. Okay, the op-amp. So you got the op-amp. Got just now you saw two resistance on top here. One connected here. Another one here. Okay, this is R. This is R. This is positive 10 volt, and this found to be because it's earthed. So this is 0 volt. So of course the potential here is positive 5 volt. So if it's negative, the input is positive 5 volt. Okay, now let's say this R is changed to 2R. What is the input and negative here will be? Anyone? This won't be positive 5 anymore. 2R and R. Anyone? What is the input here will be?
Divide 3.
Divide 3. So what is the potential here? 2R takes how much? 2R takes
6.67.
67. So the balance here will be potential is 3.33 here. Yeah, 3 volt. So potential will be 3 volt. That will be the input. Okay. So let's say you have another potential divider here. That potential divider is linked to positive. Okay, linked to positive. Okay, you have an LDR here. LDR. Okay, let's say this is positive 10 volt. Of course, this also connected to the what you call earth. Okay, now this resistance, let's say R, this LDR, tell me, okay, now tell me, LDR, when the LDR light intensity increases and light intensity rises, what happened to the resistance of the LDR? Will decrease. What happened to the voltage across LDR? Decreases. So the LDR going to take less voltage. When the LDR take less voltage, what happened to the input at positive? Increases or decreases? Anyone? See, the input voltage of the terminal is exactly same as voltage used by the resistance below at the bottom. You see, the 3.33 volt for the first case, the 3.33 volt is the voltage going to be used by the R below here. Correct? The above is using 6.67, down is using 3.33. So the input voltage going to be same as the voltage of the below resistance, 3.33 volt. Okay, so same thing go for LDR. If LDR intensity of the light exposed to a more greater intensity and the resistance of the LDR drops, therefore voltage across LDR drops, therefore the voltage going into the positive terminal will drop or rise. Will drop. So the positive will drop. Okay, so positive will drop, and more light comes in. Okay, and there is more light shine into the LDR, more greater the intensity, then the voltage across the LDR will drop down, more down, then positive will drop further. Then the output of the op amp will most likely be positive or negative. What is the formula followed by the op amp? The output voltage is equals to the gain V plus minus V negative. Okay, so tell me, when the LDR intensity, the light intensity is high, resistance of the LDR drop, voltage drop, that means V plus is dropping. V plus is dropping. Okay, V plus is dropping. What happened to the V output? V output will be positive or negative, most likely.
Negative.
So it will become negative. So output turn to become negative. Okay. If normally, it's normally, not always, normally when the output negative, that means the whatever circuit connected here is the output circuit which we haven't explored yet. Normally connected with the, maybe for this case, because it's the LDR, right? LDR may be a street light. The street light bulb won't be light up if its output is normally, if it's negative. Normally I say, not always. Negative output means normally the light bulb will be switched off. Okay, so this is how the op amp works lah. This is how op amp works. You compare the negative input and the positive input. So check the output. Okay. Any questions from here? Okay. Okay, no questions. Can now tell me, can we use this circuit to switch on the light bulb, the street light bulb, in the evening? Is it this circuit is workable to switch the light, to switch the light, the street light, okay, the street light in the evening? Possible or not? In the evening, what happened to the light intensity? In the evening, what happened to the light intensity? Intensity will lower. So resistance will get, the LDR resistance will get higher. So voltage across LDR will get higher. So positive input will get,
more
greater. So output going to be most likely
positive.
So it's going to give a positive output. So light bulb can be on. So we fix the LDR down here. So it works for to on the street light. Okay. So not every time you can see in the morning at 7 o'clock, around 7 o'clock. In the evening, at around 7 o'clock, you can see the street light is switched on by itself. Not someone is on it, but actually the sensors is the one doing the job. Okay. Definitely the LDR. LDR is kept inside. Okay. Any questions so far about this? Okay. So we go back to the slide. Okay, the slide. Okay, so let's see here. Okay, so this is all about the circuit. The LDR could replace by, yeah. Okay, Okay, so the LDR could be replaced by other sensors provide alternative sensing devices. But currently we use LDR because we want to go for a street light. It is usual to connect a potential divider each of two inputs. One potential divider provide a fixed voltage at one input. Yeah, one input we fix the input. Normally the negative we fix it by having a fixed resistance. We don't want the negative to change. The positive will be left with the sensor. So sensor can change one of the input, most probably like positive. Okay. So yeah, so that's what the first paragraph says. One potential divider provides a fixed voltage at one input, while the other potential divider provides a voltage dependent on sensor. Okay, sensor. So yeah, so I go straight to the next paragraph. If LDR resistance greater than F, V positive going to be greater than V negative, the output going to be positive. Okay, this is important. You need to understand. Okay, when the LDR resistance is lower than F, V positive smaller than V negative, output will be negative. Okay, it can be seen that the situation choice in F the comparator. Okay. In this case, the op-amp act as a special character we call what? Comparator. It acts as a comparator. We compare the input of negative and positive. It just gives either positive or negative output. Output could be positive or negative. No like zero. It always positive or negative. Positive means on the output device. Negative means switch off the output device. Okay, so it acts as a switch, or another word, it acts as a comparator. Okay, comparator. Okay, so any questions from here? Okay, no questions. I want to ask you one question. What, let's say this is the circuit has been used in the to on the street light in the evening. Okay, let's say the operator in the who are fixing this circuit, he mistakenly put this LDR not here. He put the LDR here on top and put a fixed resistor here. He shouldered the fixed resistance at the bottom. Okay, here the fixed resistor. This is a fixed resistor. Okay, now tell me, what type of problem you're going to face if this circuit is fixed into to switched on the street light? Anyone? What problem you faced? LDR is fixed on top. What will happen? Is it going to switch on the light in the night or in the daytime?
Daytime.
In the daytime. Good. So it's going to switch on in the daytime. Why? In exam they asked you to explain the mechanism. So when light intensity rises, I do here. When the light intensity rises, the resistance of the LDR will decrease. So voltage across LDR will decrease. The voltage here will decrease. So the voltage of R will increase, because these two resistors is the one sharing the 10 volt line. This is a 10 volt. So the input V positive will rise. When it will rise? In the morning. In the morning, when the intensity rises, when in the morning at 7 o'clock. At 7 o'clock in the morning, the V positive will rise, so output most likely become positive. So the light bulb going to on in the daytime. In the daytime, if it's LDR fixed on top, so it have to be on bottom. In exam, they will ask you to, they put the LDR, they will ask you to explain, what happened to the output circuit? Is it going to on in the night or in the daytime? So you have to explain. How do you start explaining? Start from intensity. Intensity check rises, resistance what happened, voltage what happened, therefore what happened to the input. So V positive greater than V negative, you have to tell that in an equality sign. Then you say output positive or negative. Okay. Okay, class. So now this is important. So far, if you understand what I'm trying to say to you, you should be able to answer this question. Okay. So this question is again, you need to think carefully. We're going to use this operational amplifier as a fire alarm circuit. We're going to use it as a fire alarm circuit. Okay. So I want to replace this LDR with a fixed. What sensor do you use if it's a fire alarm circuit?
Thermistor.
So you use thermistor. So we're going to use a different sensor. We're going to use thermistor. Okay, tell me now. We don't want LDR. Okay, we don't want. Okay, I fix the LDR. I change it to as a fixed resistor. Fixed resistor. This is a fixed resistor, not more LDR. Okay. I think better I go to the. Okay, yeah. Okay, let me go to the whiteboard better. Okay. Okay, clear this. Okay, so the circuit is here. Okay, you have one. This is for the negative. You get another one here. Okay, and here. Okay, sorry. Okay, this is connected to positive. Okay, it's also connect earth, and you have the power supply. I don't want to draw the power supply. It's connected here. Okay, tell me now. You want to replace one of the device as a thermistor. I'm going to put thermistor. Okay, I put here fixed resistor. Okay, tell me one or two. You place your thermistor.
One.
Yeah, one. One. Is it one is your thermistor? So here you fix your thermistor. Everyone? Okay, let's see. Okay, if you put your thermistor here and the temperature rises and there is a fire in the room and heat reach this circuit, temperature rises, what happened to the resistance of the thermistor? Will drop. So voltage across thermistor will drop. Okay, voltage across the thermistor will drop. So voltage here will drop. Voltage in the second one will rise. So the input voltage V positive will rise because voltage in input positive is following the voltage of the below resistance one. So V positive rise. So the output most likely will be positive. The output is equals to A V plus minus V negative. So V plus is most likely going to be greater than V negative. Yes, good. So the thermistor have to be at the spot 1. Okay, those who are remember, those who are thought of 1 should be the correct position. Very good. That's your answer. But in exam, you need to explain the entire process. Why you need to place on top. Start with the temperature rise. Temperature rises, resistance of the thermistor drops, the voltage across the thermistor drops. Therefore, voltage input of positive rises. So V positive most likely greater than V negative. Output going to become positive. You got to switch on the alarm. Each and every part got carries mark, around 3 marks, I think, for the explanation. Okay. Okay, good. So those who get 1, thermistor, great, got idea. Okay, now I'm going to add more. Okay, this circuit, okay, it works for an alarm system. But let's say this is your room. This is your room. Let's say this is your room. The fire happens at this corner. The fire happens at the right corner, and the circuit of alarm is fixed at the top left corner. By the time the light, let's say it happens in the daytime. The fire happens in the daytime. Daytime is already bright. Okay. Sorry. Yeah. Sorry. Not the daytime. In the night. In the night. I see the fire happens in the night. By the time the heat reached the small fire reached the sensor, because thermistor only can work when there is a temperature change. But temperature to reach the corner of this building takes time. Okay, so maybe the light will reach first. The light intensity, the light, because it's a night, the room is off, night. So suddenly a small light appears. So we want the sensor also detect the light intensity and switch on the alarm before the temperature rises. If temperature rises, I think the fire is already quite big, so already might be too late. So my question now is,
you need to add what sensor also in this circuit to work more efficiently, because we want to check the intensity of light also to what do you call, to on the alarm. What sensor do you use? Of course, again,
LDR.
LDR to be used.
Okay, now question is, where do you fix LDR? Okay, the 1 and 2, don't use 1 and 2 anymore. The first potential divider works for LDR. I want to fix the LDR in the 3 and 4. Okay, 3 and 4. Okay, tell me, 3 or 4 you fix LDR?
4.
At 3, 4.
Everyone agree? Is it 4? We put LDR here. We put LDR here. Is it works for? Okay, let's see. So if you put LDR here, what happened? Okay, when the light intensity rises, suddenly burning starts, the light intensity rises. What happened to the resistance of the LDR? Decreases. The voltage of the LDR, what happened? The voltage of the LDR also decreases. And the voltage of LDR decreases. What happened to the negative input? This is very important. What happened to the negative input? Drops or rise?
Decreases, sir.
Decreases. Good. So negative input decreases. So according to the, what is the formula by the op-amp is, output equals to gain V plus minus V negative. Yes, V negative is dropping. When V negative is dropping, most likely the V plus minus V negative is going to be positive, because V negative is dropping. You want to make output positive, two choice. Either you raise the V positive or you decrease the V negative. Okay, so here V negative is dropping. Yeah, the alarm will work.
So this is the best circuit. So LDR fixed here, resistor fixed at the top. So this is the good circuit as a fire alarm system.
Okay, it can sense light intensity, it can sense heat, both. So it can make the op-amp to give output. Output will be an alarm, so alarm will switch on.
Any question from here? Okay, if you understand up to here, good. I think the main part is this potential divider, the sensors one. Okay. Okay, class. I clear this, a lot of things. Okay. So I need to draw many times. Okay, again, negative, positive. I go back to the street light. I go back to the street light.
Street light, the LDR was fixed here. Okay, LDR is fixed here. The resistance is here is given 5 ohm. Here is given 5 ohm. Okay. Okay. So the LDR fixed here. So when intensity rises, resistance LDR drops. The voltage across the LDR drops. So the V positive drops. So output going to be intensity rises, resistance drop, voltage LDR drops. So output voltage going to be drop. So V positive going to drop. So output going to be negative and negative. So my negative, what happened? What happened? The street light will be off. Okay, the light bulb will be off. Okay, light will be off. Okay. Okay, let's say light will be off, and in the evening, the intensity get dropped. Okay, I go for the evening one. The evening, the intensity drops. Resistance of the LDR rise. Voltage across LDR rises. So output of positive will rises. So this become positive. The light will on now. On now. Okay.
The question now is when the technician go and fix this circuit, okay, the engineer when he fixes this circuit, okay, he found that the street light is come to act. It's switched on at around 7:30 p.m. The street light only become on at 7:30 p.m.
Okay, now the question is, the engineer want the light to on at 7 p.m. You want the light to on a little earlier, 7 p.m. You don't want to be 7:30. Okay, you want to on at 7 p.m. Okay, tell me, what you should do to the circuit so that it on at 7 p.m. First, resistance 1, 5 ohm here. You increase this resistance or decrease this resistance so that it can on at 7 p.m.
Increase.
If you want, yeah, increase or decrease. Can't hear you.
Increase.
So increase this 5 ohm. Is it increase? Okay, let's see. Why you increase this 5 ohm? Because the formula followed by the op-amp is what? The output equals to gain V plus minus V negative. So if you want to on at 7 p.m. okay, if you want to on 7 p.m. you must make the V negative smaller. Okay, you must make the V negative smaller. V positive you can't do anything because it's by the sensor. So we make V negative smaller. So the V negative here must make it smaller. How to make V negative smaller? So the upper resistance must make it bigger. Yes, correct. The upper resistance must make it greater, so that the voltage here is smaller. Smaller voltage at the bottom resistance will be the voltage input to the negative. Then therefore it will be, output will be positive
earlier in a low intensity. Yes, good. The resistance have to be on top. Okay, so this kind of question they will ask in exam. Any questions, guys, so far? Okay, so yes, I go back to the circuit. Okay, that's what this slide, I hope I successfully explained to you. Okay, let me go to the next one. Okay, this is fine. We don't do this. We go to this. Okay, 1 minute for you. Look at the circuit above. Look at the table down. Does it make sense for you? Just read the question. Okay, so I hope you understand the circuit. Okay. So they're giving input 2 volt. That means here they give 2 volt. So that means the voltage here will be 2 volt. Okay, the voltage here also will be 2 volt. I think both positive input will be 2 volt. Okay, the resistance here, the 3 resistance here was fixed as such as the potential at A is positive 5. Potential at B is 3 volt. You now use your op-amp formula. For the first op-amp on the top, the positive is 2 volt, the negative is 5 volt. So the output will be positive or negative. Who's greater? V positive greater or V negative greater? V negative greater, right? So output will be positive or negative? Will be negative. Okay, output will be negative. So when output is negative, down voltage is how much here? A is 0 volt. 0 volt, negative volt. Current will flow from always, current will flow up or down? Anyone?
Up.
Current will try to flow up. Current always flow from high potential to low potential. So current try to flow up because we have a LED here. LED is actually a diode, light emitter diode. LED is a reverse bias or forward bias here. In this case, it's a reverse bias. So you block the current from flowing. So green won't light up. Green won't light up. Okay? Because green LED is in reverse bias. What happened to the rate? The bottom one. Positive is 2 volt, negative is 3 volt. So output still
Negative.
negative. So current still want to go up. So rate also cannot light up because it's reverse bias. So rate also won't light up. Okay, so both wrong. Okay, now light up. Okay, now if the input voltage become 4 volt, become 4 volt, what happened to the, okay, now I clear this. So, okay, now the input become 4 volt. Input become 4 volt. What happened to the here 4 volt? Here 5, here 4. So output will be still negative.
Negative.
So green won't light up. So green never light up. For the lower volt op-amp, 4 volt. Here also will be 4 volt, but up is 5 volt. Positive, still negative greater than positive. Oh, sorry, positive or negative, which is greater. Oh, this is 3 volt, this is not 5 volt. Negative is 3 volt. 3 volt, 4 volt. So positive greater, so output will be positive. Current will flow down. Current will flow in the rate. So rate will start to light up. When you give 6 volt, both will light up. Okay. This circuit can be used for a fire alarm. Can be used for a fire alarm also. The 4 volt to the 2 volt, 4 volt, 6 volt was created by a sensor. Of course, in this case, the thermistor is used in a potential divider technique. So the thermistor gives the voltage input into the op-amp. So op-amp, if the first red light to be on, or red light on, means something fire is occurring. Something fire is occurring. 6 volt means maybe 2 on, maybe the fire is getting bigger or what. Okay, we can use the sensors. Any questions from here? Okay, what is the function of operation amplifier here? Acting as a comparator. Call it comparator. Okay. Okay. So that's the first part. Okay. So that's the sensors and everything. Sensors and everything. Okay. So we already done the first part of the operational amplifier. Okay. The next one is going to be this. Okay. This called feedback. Okay. Let's say you have an operational amplifier. You put a sensor as shown in the just now earlier, LDR and everything. The output is always saturated. It's always saturated. Okay. Means what? Means what I'm trying to say is okay, what I'm trying to say is, let's say you have a negative and you have a positive. Negative is fixed with the resistor. Positive one is fixed with the resistor. And one, let's say you connected to a microphone. And it was earthed. Okay, earthed. Microphone. Okay, let's say opera singer. Let's say she's let's say talking. Okay, she's talking here in the microphone. So, or singing a song. What the microphone does? Microphone, will create the sound into electrical energy. So there will be a voltage created here. Okay, and the voltage rises, the input positive will rises. Okay, so if the opera singer create a signal of sinusoidal like this, okay, change the color. If she produces a wave like this into the positive, okay, the output is A V plus minus V negative. The V negative we make it as low as possible. Okay, so maybe we can put it as 0. So whatever input in the positive will be produced here. So output will be of course positive, but it will be saturated. Saturated means what? The power supply, let's say, is positive 10 volt. Positive 10 volt. So let's say input is a curve. The curve, it will saturate to what type of shape? It's going to be like this. It's going to be like this. It is going to saturate to positive 10 volt. Okay. Opera singer is singing, oh hello, whatever tone lah. It says hello. This pattern, right? This pattern. Excuse me. Will be saturated. Saturated means what? That's what op-amp does. What? Because the gain is very big, 10 to the power of 5. You give whatever voltage, whatever changing voltage you put, the gain is because so huge, you're going to saturate to 10 volt. So now tell me, can we use this comparator in a music industry to amplify the signal?
Nope.
You can't. Why? Because the op-amp won't give the same pattern of the input signal. Let's say you go for a patient who got a heart problem, connected with the electrode to a operational amplifier and to the CRO. Let's say the heartbeat becomes lapped up, whatever. Okay, lapped up. This signal. If we get into this operational amplifier, before the output will be how? It's going to be like this. So the patient will get the kind of this kind of a pattern will be traced on the CRO. Because operational amplifier going to saturate the input. Why this happens? Because the gain is huge, 10 to the power of 5. So we got a big problem. For a switching system like alarm, it saturates good. This is like on, this is like off, good for alarm. Alarm, street light, good, like a switching system. But when it comes to like medical and in the musical industry, the pattern of the wave input need to be retained. Okay, if the heartbeat is like this, after passes the op-amp, make the heartbeat quite amplified. We want the signal to be amplified because heartbeat, the sound is very small when reached from the electrode to the CRO. So in between they put the op-amp to strengthen the signal. So the op-amp must amplify the signal without altering the pattern. So how we can do that? How we can retain the pattern when we pass the op-amp? What is the problem we face? The gain is huge. So what do you have to do if you want to retain the pattern? The gain must drop or rise. The gain must be reduced. So how to reduce the gain? We can reduce the gain maybe up to maybe 100 or maybe 10. If you make the gain as 10, so this wave can be amplified for 10 times, and the pattern can be retained. So the biggest problem the industry facing is how to reduce the gain of the op-amp. So they say we can achieve reducing the gain and retain the pattern by using something called feedback. Okay, you see, if you do feedback, you can achieve 3 benefits. Okay, I straight go to the benefit before I discussing this. The benefit is, this is the 3 benefit. Okay. The main benefit is the, okay, oh, this is not less distortion. Okay. The main benefit is the, it's not written here. The main benefit is the gain will be, the gain will be reduced. Okay, the gain will be reduced. Okay, so the first, yeah, given a 3 benefit. Yeah, let me explain this 3 benefit. Yeah. If the, okay, I start from here. This can be achieved by feeding back part of, okay, this I haven't teach you yet. The reduction of amplification may bring following benefit. The first is the increase in the range of frequency of which the gain is constant. Okay, what is this first point trying to tell? Okay, to understand this point, there is one graph missing in this slide. Okay, you have to get one graph here. The graph which is missing in this slide is the graph gain versus frequency. Please add into your notes. Gain versus frequency. The gain of op-amp versus frequency. The graph will be looks like this. Is 10 to the power of 5 here. Okay. So this is the gain versus frequency graph for the op-amp. This graph is fixed. Okay. The flat line, you know, the frequency up to here, this frequency, this is called bandwidth. It's called what? This is your bandwidth. What is bandwidth? Bandwidth is the range of frequency where the gain is constant. This is called bandwidth. Okay. By doing feedback, the gain will drop. It won't be anymore 10 to the power of 5 any again. It might be, we can drop to, let's say 100. The gain we can drop by doing feedback. So now the gain, let's say 100. The graph, new graph will be here. The graph will be here and following this line. So what happened to the bandwidth now? What happened to the bandwidth? The bandwidth increases. The bandwidth increases. So an increase in the range of frequency of which the gain is constant, the bandwidth will be increased if the gain is decreases by doing feedback. This is called feedback. If you do feedback, the benefit of the first feedback is bandwidth is raised. More lower the gain, you bring 10, the bandwidth get even longer, getting longer and longer. Okay, so good to have big bandwidth. Okay, as I said, why bandwidth is important? The opera singer sings a sound, let's say the bandwidth, let's say, is 15,000 hertz. The opera singer sings a sound less than 15 hertz, let's say, less than 15 hertz, the sound is produced. The bandwidth, let's say, up to 15,000 hertz. Okay, so 15,000 hertz, the gain, let's say, fixed 10 times. So whatever the song she's singing, it will amplify for 10 times. It will amplify for 10 times. Okay, in the hall, everyone going to listen a loud sound of 10 times. Suddenly, if the opera singer increases the pitch, she rises the pitch. That means the frequency is getting higher. What happened? Let's say the pitch rises more than 15,000 hertz. What happened? It already out of the bandwidth of the op-amp. The bandwidth, so therefore the gain of this op-amp won't be 10 anymore. Maybe suddenly become 5. So if become 5, what happened? Suddenly the loudness of the sound lower, 10 times 5. So the audience will can't enjoy the song. The amplifier was amplifying for 10 times. Suddenly the pitch has been raised out of the bandwidth. So the op-amp won't work at its optimum level. you can't give gain as 10 as last time. The gain will drop as according to this graph. You see, if you go out of the bandwidth, the gain will drop. When the gain drops, it's not nice to hear the song in the hall. So good to have a big bandwidth. How to get a big bandwidth? You drop the gain. How do you drop the gain? By doing feedback. Do feedback. Okay, so that's the first benefit. Okay, first benefit is what? The bandwidth can be increased by reducing the gain. Okay, just reduce the gain by doing feedback. Okay, any question about the first one? Okay, no, okay, next benefit we get by doing feedback is less distortion. What is meant by less distortion? As I said just now, the opera singer, if he raise the frequency 50,000 hertz, the gain suddenly dropped to 5. Suddenly the sound, which is quite loud by 10 times, suddenly dropped to 5 times. So it's a distortion. It's a distortion to the audience. So if you increase the bandwidth, it's less distortion. And the third, we said, because less distortion, we said greater stability for the circuit. So that's why we do what? We must do feedback. Okay, we must do feedback. Feedback does these three benefit. You must do feedback operation amplifier if you want to retain the pattern of the input signal. Okay, let's say scientists want to know how the sound produced by a bat. The sound produced by a bat maybe have a specific pattern. The pattern you need to amplify. The type of amplifier you must use. The amplifier must have a feedback. If it has a feedback, the gain is dropped. So when the gain is dropped, the saturation won't happen. The op-amp won't saturate. It won't give a square wave graph. So the pattern could be retained. Okay, that's why we do feedback. Okay, so three information. So why you need to do feedback? You want to retain the pattern. Then you do feedback. Works for what? For musical industry, for medical, to check the heartbeat, for science, for discover all kind of sounds produced by the animal. You want to research it. You have to use the op-amp with feedback. Any question, guys, so far? Okay. So I go back to the slide. Okay, now, what is meant by feedback? Okay. Feedback, just one wire. From output, one wire is connected into the input back. You just transmit one wire into the input. What is feedback? This is the point you have to remember. Feedback is the process of taking some or all the output of amplifier and adding into the input. It's called feedback. Okay, adding into the input. So this is the formula proving that the output over input, it seems getting smaller. The gain drops because beta is the fraction of the output has been channeled back into the input. So you see this formula, the input to amplifier is increased, beta V out has been added into the input. So when we make V out of V in this formula, we got this formula. And beta is going to reduce the denominator here, the 1 minus A naught beta. Denominator going to be smaller than 1. So, smaller than 1. Beta is A naught, 1 minus A naught beta. 1 minus A naught beta. So, beta is a fraction. 1 minus going to be smaller. A naught. So, the gain decreases. The gain found to be decreases. Okay, so by doing a feedback, okay, by doing a feedback, because the beta is a negative input, down number get bigger, more than 1, so the gain drops. Okay, the gain drops. So doing feedback, the gain from 10 to the power of 5, won't be 10 to the power anymore. It will drop to whatever value you can desire. You can fix it. Okay. So yes. Okay, now. Okay, now our story all about feedback. Okay, feedback. So this is a feedback. Create two type of amplifier. The first amplifier we call inverting amplifier. Inverting amplifier. Inverting amplifier will have a feedback. This is the feedback resistance. Develop a resistance is a feedback resistance. Okay, this is the feedback, and you have a Rin and RF. Okay, so this is a inverting amplifier. Inverting. Why we say inverting? Because the input is at negative. We give the input at negative. Positive is normally earthed. Earthed is already earthed. Okay. Inverting amplifier have two character. The input will be at negative. It will have a feedback. If you have a feedback and the input as negative, it's an inverting amplifier. Inverting amplifier means you give a cost graph. You see the signal is a cost graph. After you get into the operational amplifier, the amplifier will invert the signal. The cost graph become what graph? Negative cost graph. So the cost become negative cost. That's why it's inverting. If you give a sine graph, you get a sine graph, you're going to invert to negative sign. It's going to invert the signal. It's called inverting amplifier. Okay, it's called inverting amplifier. Okay, now, so let's describe this. So now, if you give a cos, the pattern won't be a square wave anymore. It will be a cos again. Why? Because the amplifier now has a feedback. Therefore, the gain is quite small. Gain is very small, so you can retain the pattern. Okay, retain the pattern. Because you will give a power supply. Right? The power supply, let's say, give positive 10 volt. So the input signal, let's say 2 volt. Okay, you put gain as, let's say, 4 times gain you put as 4 times. The 2 volt maximum you're going to reach is 8 volt. So still within the power supply range, So you get the pattern, you retain the pattern. If the gain is 10 to the power of 5, this is definitely going to be a square wave because you're going to saturate to 10 volt. So that's why feedback. Okay, class. So now let's discuss the important one. You need to know this derivation. Okay, you have to know this derivation. Okay, these derivations to get the gain formula for inverting amplifier. Okay, for inverting amplifier. The gain formula for comparator is 10 to the power of 5. Fixed, never change. But for inverting amplifier, the one have a feedback, the gain as a formula, the V out over V in as a formula. The formula is found to be negative RF over R in. What is RF? Is the feedback resistor. The feedback wire, whatever resistor is connected, this is called RF, feedback resistor. And the resistance in the input is called R in. Okay. So now, how they got this gain formula, the derivation, you have to know. Okay, let's spend 3 minutes to get this derivation correct. Okay, first, they start the derivation by saying I in equals to IF. Okay, what is I in equals to IF? You see this, the current flow in the R in is called I in. And the current come to this P junction. Is there any current flow into the op-amp? Is there any current flow into the op-amp? The current flow into the op-amp is how much? 0. No current flow into the op-amp. Why? The impedance is infinite. So no current flow into the op-amp. So according to Kirchhoff's first law, whatever current flow into the junction, same as the current leaves the junction. So because no current flow into the op-amp, whatever current flow into the R in is the same as current go to the RF. That's why I in is same as IF based on Kirchhoff's first law. Okay, first law. Okay. So I hope you understand the first line. So now you see, for the I in, the voltage here is V in. The voltage at P is always 0 volt. It becomes 0 volt. Okay. Why this becomes 0 volt? Why this becomes 0 volt? There is a 3 marks question they will ask. Why point P is 0 volt? Okay. In other words, this point P call a name, special name called virtual earth. Call it as a virtual earth. You know it's earth. Earth means you are connect a wire to the ground. This is earth lah. Earth means understand what is 0 volt lah. The voltage at earth is 0 volt. And this point P called virtual earth. Why virtual? Actually, we are not connecting it to the ground, but it still create a 0 volt at that point. Okay, why we call it as virtual earth? So this is the explanation you have to tell. Okay, it could be a 3 marks question. Explain why P is a virtual earth. What is meant by virtual earth? Okay, why it's a virtual earth? First, V positive is 0 volt, 0 volt. To ensure amplifier is not saturated. To avoid what? To avoid the output saturation, the V negative and V positive must be about the same. The positive input and negative input must be about the same to prevent saturation at output. Okay, because you know what? Op-amp easily can be saturated if there is a big difference in the input. Okay, so it should be 0, 0. So V negative and V positive must be about the same, 0. Okay, V negative as V must be about the same. Therefore, P is same as V positive voltage, which is 0 volt. Called virtual earth. Please add one point here, which missing in the mark scheme, missing in this slide, which given 1 mark in the mark scheme is, before you tell this, first thing you must tell the op-amp as huge gain. That's 1 mark. The operation amplifier has huge gain. Okay, that's 1 mark. Okay. To ensure amplifier not saturated, V negative must be same as V positive, 1 mark. Okay. Because V positive is 0, therefore V negative also must be close to 0, called virtual earth. Okay. It's virtual earth. 3 marks question. They will ask what is meant by virtual earth. Okay, now I go back to the diagram. So when the current flow into this P, the current will flow up to the RF. So I in equals to IF. But now I in, right? The I in. What is I? Current. Current is V over R. Potential difference divided by the resistance. Potential difference is the what do you call the potential difference? What is the potential difference along this P? V in minus 0. V in is at this point. After crosses the R in, Vp, which is 0 volt, is the final voltage. So what is the potential difference with the R in? V in minus 0. So V in minus 0 is the voltage difference over R in, the resistance R in, and therefore you get I in. V in minus 0 over R in is the current flow here. Okay, now go for V out. V out is here, coming out V out. What is the potential difference across RF? 0 minus
V out.
V out. Yeah, so you put 0 minus V out, the potential difference over the RF. RF. Yeah, so this is the IF current. So I in same as IF, we can written in terms of voltage over R. After that, just rearrange V out over V in, you get negative RF over R in. Yes. So this is the what formula? The inverting amplifier, or the V out is pi. Yeah, this okay. The gain formula for inverting amplifier is negative RF over R in. RF is what? The inverting resistance. R in is the the input resistance. Okay, so the under electronic world, now we have a big relief. The big relief is the gain can be controlled by us. The human can control the gain of the operational amplifier just by manipulating the resistance. You manipulate the resistance, you can get whatever gain you like. Okay, you know, in the hall, when someone is talking on the stage, okay, if the loudness is not enough, someone technician go and find the knob, the volume knob. Actually, what the technician is doing is just changing one of the resistance of the circuit. I think it's changing most probably changing the R in. Tell me, if you want to get more loudness, the gain must get big. To increase the gain, the R in must decrease or rise.
Decrease.
So it decreases the R in. So indirectly, when it turns the knob to a high volume, inside the circuit, what happened is decreasing the R in, so that the gain is rise. So the output signal is more greater amplitude, more louder. That's what happens inside the circuit, RF over RN. Okay, class, any question from this slide? Okay, yeah, I know a lot of stuff you are learning. Okay, the rate of learning is quite high for today. Okay, so what you need to know from this slide is inverting amplifier. What is inverting amplifier? A type of amplifier which has a feedback. Why you need to have a feedback? Because to drop the gain, therefore the pattern of the input signal can be retained. Okay, and the inverting amplifier, what is meant by virtual earth? To prevent the op-amp has some infinite very high gain. So to prevent saturation, V negative must be same as V positive, because V positive is 0 volt, therefore V negative also 0 volt, called virtual earth. And the gain derivation, you have to know, it's like a 2 or 3 marks derivation. And the input and output will have a phase difference of pi radian. If you give a cos input, the output will be a negative cos for inverting amplifier. Okay, so two feature, how do you know it's an inverting amplifier? The input must be at negative, must have a feedback. That's the inverting amplifier. Okay. Okay, so another 10 minutes, we can stop the lesson. But before that, okay, let's do some questions about this inverting amplifier. Okay, so inverting amplifier, current either flow this way to the right or current will flow to the left. Theoretically, no current flow into the operational amplifier because it has a input infinite impedance. Okay, impedance means resistance to the current flow. Okay, so V out or V in is negative RF over RE. Okay. Let us one question. So this is a inverting amplifier. How do you know? The input is at negative, and second is there is a feedback. Okay, there is a feedback. Okay, this feedback called negative feedback. It's a negative feedback. Okay, why we say negative feedback? A fraction of all the output channel back to the negative input or inverting input. It's called negative feedback. This is also quite common. They ask an example. What is meant by negative feedback? A fraction of all the output channel back to the inverting input. It's called negative feedback. Sometimes they call what is meant by feedback. Feedback means a fraction of all the output channel back to the input. Don't specify inverting or non-inverting. Then it's a feedback. If they say it's negative feedback, you must specify. Fraction of all the output channel back to the negative feedback. Okay. I think most of your circuits, all the circuits are negative feedback like okay, your syllabus. Okay, that's the first question. 22 kilo ohm, 10 kilo ohm. Calculate the output voltage. Input is 0.44. So do you understand the working? Output is the gain times the input voltage. Yeah, V out over V in is the gain one. In this case, the gain is what? Negative RF over R in. So where is the RF here? 22 is your RF. 20 so 22 divided by 10 is your gain. So 22 divided by 10 is your gain. So it's negative. Of course, gain is inverting the graph. So negative 22 over 10 is your gain times the input voltage 0.44. This is your output 0.968 volt. Very small because we managed to drop the gain. Gain is only 2.2. Last time it was found to be the gain is 10 to the power of 5. Now we can control it to very low gain. So yeah. Any question from this slide? Okay, another one. Class, look at the diagram and the question. Try to understand. The diagram shows an inverting amplifier. Find the gain and the output. Gain how much? The 10 kilo ohm is your RF.
-5.
So it's negative 5. So negative RF over R in 10 divided by 2 negative. It's your gain. So output is gain times the input. Input is 0.2 volt, so you get negative 1. Yeah. So that's the gain line. Okay. Next one. 10 and 5. What is the gain? Negative 2. Gain is negative 2. So the input given is positive 0.5. So output will be what? Gain was negative 2. So 0.5 times negative 2, negative 1 volt. So input is positive 5 volt, output will be negative 1 volt. Okay, when V in is positive, V out will be negative because it's the inverting amplifier. If it's negative 1.3 volt times the gain negative 2, output will be 2.6 volt. Okay. Okay, next question. Okay, class. Yeah, another one question. The circuit of amplifier, ideal operational amplifier is shown in the diagram. State the name of the type of amplifier circuit. So what type of amplifier is this? This is a inverting amplifier. How do you know it's inverting amplifier? The input is at negative. That is a feedback. So it's a inverting amplifier. Okay. State the name of this type of amplifier. Why the point P is referred to as virtual earth? It could be a 3 marks question, as I told you. Why the P is considered as a virtual earth? Gain of op-amp is very large, 1 mark. In order that the amplifier does not saturate, 1 mark. The inverting must be approximately equal to the voltage of the non-inverting. Sin V positive is earth, 1 mark. So V negative also must be earth, virtual earth. Please memorize this definition, this description for virtual earth. Okay. So B, show that the gain G amplifier circuit is given by the expression G is negative R2 over R1. The derivation to get the gain formula. How do you derive? I in equals to IF. Okay, no current flow into the op-amp. So V in minus 0 over R in equals to 0 minus V out over R in. The earlier derivation I showed you. You have to show that to prove this equation. Okay, the solution is here. The current is the same. So then you got this formula. Okay, guys, any questions from this slide? No, Okay. Okay, plus. So this is the last one. Then we can stop. Okay. Last question for today. Read the question, try to figure out the answer. 1 minute for you. Okay. So you get the idea of the question. Determine the voltmeter reading light intensity such that LDR has a resistance of 100 kilo ohm. What is the voltmeter reading? That means another word they're asking what is the output voltage. What is the output voltage? And the LDR has a resistance of 100 ohm. The R2 is 50 ohm. The R1 is 5 ohm. The input is 1.2. So, how do you find output? Output over input should be the gain. So, output over input is equals to negative RF over Rin. Okay, then you can find the input. Output is 1.2. Rin is 5 ohm. RF is now the difficult one. RF how much? The 150 was connected in parallel. So you find the effective resistance. 1 over 100 plus 1 over 50 reciprocal. That should be RF. Then you can find the V out. That's the answer given here. So feedback resistance is 33.3. 1 over 100 over 1 over 50, I think reciprocal you get 30.3. So gain is negative 6.66 times the 1.2, so you get negative 8 volt. It's the output. Okay, so do the same thing for 10 kilo ohm. Same technique. Okay, my focus in this question is the part B. Look at part B. The light incident in the LDR is provided by a single lamp. Use your answer in A to describe and explain qualitatively the variation of the voltmeter reading as the lamp is moved away from the LDR. In other words, the light intensity drops. What happened to the V out? Drops or rise? How to know? V out or V in is the gain. Yes. So what happened to the gain line directly? When the intensity drops, the resistance of the LDR drop. When the resistance of the LDR drop, when the intensity drop, the resistance of the LDR rise. So therefore, what happened to the RF value? What happened to the RF value? Anyone? What happened to the RF value? RF value rises. So gain rises, so the output should rise as well. Okay. So that's the answer here. Moving the lamp away decreases the light intensity. LDR resistance, feedback resistance increases. Gain increases. Voltmeter reading increases. Okay. So this is like a 3 marks question. Any part you don't understand in the working? Okay, class. So yeah, that's today's lesson. Okay. So today you learn about comparator, how to fix the sensors, so that how to work the alarm properly. And we talk about why the necessary to do feedback, because to drop the gain, therefore to have these 3 benefits. bandwidth increases, less distortion, more the pattern can be written. Then one version of the feedback is the inverting amplifier. What is inverting amplifier? Input is at negative. There is the negative feedback. There is the feedback. That's the inverting amplifier. The derivation of the gain formula, you must derive negative RF over in. Yeah. Then which led to our calculation just. Okay, class. So any questions? No questions, eh? Okay, I post these videos today lah. Try to understand it more. Maybe you can view back. The Monday we will continue from there. We already done 60% of this topic, 60 to 70% of the topic already. But to proceed, you need to understand this fundamental. Okay. If you don't have questions, we can stop here. No questions.
Thanks.
Okay, see you then. See you on Monday.
Thank you.
Thank you. Bye.